You plug your phone in every single night, but have you ever stopped to think about how that electricity gets from a power station maybe hundreds of miles away, all the way to that little plug in your wall? Well, the answer is the national grid, and today we're going to pull back the curtain and uncover the absolute genius behind how it all works.
It really all boils down to one simple question. Why do those giant pylons that you see marching across the countryside carry electricity at such a ridiculously high voltage? 400,000 volts. I mean, that sounds incredibly dangerous, right? So there has to be a really, really good reason for it.
And that reason is to solve a massive energy waste problem. Seriously. Without this high voltage trick, a huge chunk of all the electricity we generate would just disappear as heat before it ever even got close to your home.
And this gets us to the heart of what engineers call the power transmission problem. It sounds simple, but getting electricity from point A to point B efficiently is one of the biggest challenges in all of modern engineering.
Okay, so here's the basic physics. You know how your laptop charger or phone charger gets a little warm when you're using it? That heat is actually wasted energy. Now, just imagine that wire isn't a few feet long, but hundreds of miles long. The amount of energy lost as heat would be absolutely enormous. The whole system would be ridiculously inefficient.
But of course, there's a super clever solution. The entire national grid, this whole system, is designed specifically to fight that energy loss. It has a secret weapon.
So, just so we're all on the same page, when we say the national grid, we're talking about the whole shebang. It's the power stations making electricity, the huge cables that carry it across the country, and, this is the crucial part, the transformers that manage it all along the way.
So here's a quick roadmap of that journey. First, the power is generated. Then, right away, the voltage is stepped up for the long trip. It travels across the country, and then it's stepped down in a few stages until it's finally safe enough to power your kettle. That's the basic flow.
Now let's zoom in on the real heroes of this story, the transformers. Think of it like this. If electricity is water in a hose, voltage is the pressure and current is the amount of water actually flowing. A step-up transformer near the power plant is like putting a nozzle on that hose to massively increase the pressure, the voltage. This has the effect of reducing the flow, or the current. Then a step-down transformer near your home does the exact opposite. Now remember that relationship. As voltage goes way up, current goes way down. That is the key to everything.
All right, so we've seen the what. Now it's time for the how. How does this trick actually save so much energy? This is where we get into the really cool physics behind it all. I mean, really, how does just fiddling with voltage and current stop all that energy from just disappearing as heat? It kind of feels like a magic trick, but I promise you, it's just pure, elegant physics.
And here is the villain of our story, this little equation. It basically says that the power lost is heat, that's the P loss, is equal to the current, which is I, squared times the resistance of the wire, R. Now, we can't really change the resistance of hundreds of miles of cable, but that I for current? Oh yeah, we can definitely change that.
But look closer. The most important part of that whole equation is that tiny little squared symbol above the I. This is the secret sauce. It means that the energy lost as heat grows exponentially with the current. So if you double the current, you don't just double the energy loss, you quadruple it. It gets out of control really, really fast.
And that is where our heroes, the transformers, come in. By stepping up the voltage to a super high level, we can send the exact same amount of total power down the line, but with a much, much smaller current.
And because of that pesky little squared symbol in our villain equation, even a small drop in the current leads to a huge drop in wasted energy. We've basically found a loophole in the physics. That is why we use 400,000 volts, to crush the current down to be as low as possible for its long journey.
Okay, so we've solved the big energy waste problem. We've cracked the code. Now let's bring it all home and follow the electricity on the very last leg of its journey, from that high-voltage pylon right down to the plug in your wall.
So, we've jacked the voltage way up at the power station to send it across the country. But obviously, you can't plug your TV into 400,000 volts. So now, the step-down transformers have to do their job and bring it all back down to a safe level.
So there it is, zipping across the country on those main transmission lines at a mind-boggling 400,000 volts. Super, super efficient for long distances, but way too dangerous for anyone to be around.
Then, as it gets closer to our towns and cities, it hits a local substation. There, a big step-down transformer knocks it way down to something like 33,000 volts. Still incredibly high, but much more manageable for sending out to different neighborhoods.
And finally, maybe in a green metal box at the end of your street or on a nearby utility pole, one last, smaller transformer does the final job. It brings the voltage all the way down to a safe, standardized 230 volts, and that's the power that comes right out of your wall socket. So if you're going to remember anything from all this, let it be these things. 1. High voltage equals high efficiency. 2. Lowering the current is the secret to cutting down that energy loss from heat. 3. The step-up and step-down transformers are the magic pieces that make it all possible. And it all ends with a safe 230 volts AC ready to power your life.
And that's the incredibly clever system we rely on every single day. But it does leave us with a fascinating and pretty massive final question. This grid was designed for a predictable world, with a few big power stations pumping out energy. As we move to a future of wind farms, solar panels, and maybe millions of electric cars all trying to charge at the same time, how will this amazing piece of engineering have to change and evolve to handle it?